Welcome back to Retro Depot. Today we're going to be taking a look at registered logic again, and specifically we are going to be designing something with registered logic. I figured that a practical application is probably the best way to really get it into your head how you design a circuit. So let's first take a look at this. So this is a 2-bit shift register, okay? And essentially the way that it works is that obviously you have data in, you have a parallel load, a clock, data in if you have the serial input port, and then obviously a serial output, which I'm calling those two D in and D out. And we need to basically work this out so that we have the logic there in order to make this work. So I've already got the pinout planned, and I'm going to go over it at this time. First off, you have the clock pin. Now the clock pin, you're going to have to do some finagling on this to really, I guess you don't really have to, but it's definitely something that you need to keep in mind, because for an example, if you're running this at, let's assume that it's going to be 9600 baud. Let's take a Z80 system or a 6502 that's got a relatively low clock, system clock that is. You are going to have a period where the clock may be high if it's a running this as an oscillator, and your chip select signal may be low and it may go high again before the clock actually cycles low and high, just simply because of the timing difference. So you need to keep that in mind. It's kind of hard to explain, but you're going to have to do some finagling with this. So one thing that I thought about is that this clock pin should only go low when you have a situation where either the clock is low, the chip select is low, or they are both low. Now, an easy way of doing that would be to use an AND gate on the input to the clock. So on one input to the AND gate, you would have your baud clock. So let's assume it's 9600 baud because it's a very popular baud rate. And then on the other input, you have your chip select. And your output is going to go to the clock pin. So both of them would have to be high for the clock signal to be high. But if either one of them drops low, that is going to cycle the output and thus the clock to a low state. Now, if the transition with the chip select goes high while the clock is still low, that's still going to be problematic for you. But by potentially using some type of method to read the outputs from the Q pins, you should be able to tell whether or not it actually latched. But even if you decided not to do it that way and you were just going to be cycling this by hand, for an example, let's say to emulate a 74LS 166 or a 74LS 165, you could just simply use the chip select as both a writing mechanism and a clocking mechanism. So that's a pretty easy way of going about it. So we're not going to concern ourselves too much with that today. That's kind of getting into circuit design and timing, and that's not really too applicable whenever it comes to just writing the shift register. But on pin 1, we are going to have a clock. Pins 2 through 9 is our data pins, so data 0 through data 7. Pin 10 is going to be our parallel load pin, and pin 11 is going to be our data in pin. Now for outputs, we have obviously the pins 23 through 16, which is going to be the Q0 through 7, which those are mostly just used to hold the status of the register, if you will. They're not needed as outputs, although you could use them. Again, as I mentioned before, you could use something, for example, the output enable pin, pin 13, to determine whether or not this data is actually latched or not. But that's probably going to, and of course I would have to take a look at the data sheet to be able to tell you for sure, but I think that's probably going to end up wreaking havoc where it comes to trying to send this data out. I think that you would probably have problems with that. I'm not sure. We can always take a look at the pinout here, but it doesn't really tell us a whole lot. I just can't tell you. It looks like this output port here is going to be the it's going to be modified by the enable, because you have the enable here, and the input from those registers is only going to come back in my opinion, if the output enable is set. So I think that's probably going to cause problems. So it's one method, but I don't think it's really a good one. But anyhow, we're kind of getting off topic there. But we also have a start bit. So in the event that you wanted to use this, for example, say UART, we could program a start bit. And we also have data out. So we need to start taking a look at the equations here. So let's just start off with Q0, okay? And remember, we're using the .d prefix since it is registered logic. So when should Q0 go high? We already know that our clock is going to be the edge trigger for the flip-flop. So when would Q0 be high? Well, obviously, if we're writing a D. Well, so what do we have to do to write a D? Well, we would obviously turn D0 high. We would change its state to high. We would want to pull the parallel load pin low, and we would also want to, so that's when it would be high, at least when we're writing data to it. So let's do D0 and PL is low. But what other times might it be high? Well, this is where you have to actually think about the logic behind what's going on. So if we come here and we add an OR, when else would we want it to go high? Of course, this is assuming our clock is going to trigger it during this state. Well, we would also want it high if the parallel load is high and the data in would be high, correct? Otherwise, it should be low if the clock cycles, because if it's reading data in through DN, then it's only going to have two states. And if it's low, then we already know, I mean, we're only worried about when is this going to be high. So that's really what we want to do, is whenever DN is high and PL is high. Okay? Now, for the rest of these, it's going to be pretty similar. So, for Q1, it is going to be high when D1 is high and PL is high, or when D0 is high and PL is low. And we can continue to do this. So I'm just going to do that real fast. Okay, we're back. Now, I did make a small little mistake a minute ago. D0 or parallel load low, D0 and parallel load low should be a high on Q0, and the same thing with data in and parallel load both being high should be a 1. But on Q1 it's going to be D1 or, well, I'm sorry, D1 and parallel load low, or Q0 because we're using the output from this in its feedback state, and parallel load high when the clock cycles. So we have to replicate that on the remaining data outputs. So we're basically stating that on Q2, either data 2 and parallel load, or Q1 and parallel load not being active. And same thing all the way down. So we've replicated that on all 7 of the data registers. Now, the following one that we have to take into consideration is going to be the start bit. Now, this takes about the same amount of thought. When it's high, we need to think about what that state is going to be. So, obviously, if the output from Q7 is high and parallel load is high. So let's go ahead and put that down because that's an obvious state. So if Q7 and PL are high, but if we want a high start bit, then we also have to figure out how we give this data. And we only have, really 8 data pins. So how do we tell it that it needs to go high? Well, one thing to think about is if, the initial state that it needs to be in is high, then the only thing that we would be concerned about is its initial state. Well, what happens when we try to load data into the registers? Well, obviously we have to bring parallel load low. So the OR on this would be if parallel load is low, then it needs to go high. So that's going to be our logic for our start bit. Now we also have to take into consideration data out. So when is data out going to be high? Well, it's not too different. It's only going to be high if Q7, or I'm sorry, if SB is high. That's the only time, because if unless it's getting data from from the start bit here, because the way it's going to work is the data is just going to shift over with each clock cycle. So unless it's getting the data from this register here, it should never have any other state. That's the only time that it should ever have that. So realistically, and let me put it this way: you're going to have your data in, and of course we won't keep this here. We'll have to delete this. But let's say data in is going to be low. So when this shifts data out, let's say that we've latched the data and it begins shifting it out. So the start bit is going to be high and it's going to shift over into D out. Q7 shifts over into the start bit register, 6, so on and so forth. And when you finally get to the data input port, let's say we have it tied to ground, it's going to shift that low bit into Q0. And as the clock cycles, it's going to shift on down, turning all of these low up until the point that it gets to eventually the start bit and then the data out pin. And this clock may still be going up and hot, or up and down, up and down, up and down, but it's just feeding this data straight across. So the only time that the start bit should have a high state is if we are loading data, okay, or if the data is being shifted over. And the same thing with the data out. The only time that it should ever have a high state is if we are shifting a high bit into the data out from the start bit. Does that make sense? I hope so. So that's the logic right there. Very simply, we have created what I think is going to be a functional shift register. Now, again, as I mentioned before, we do have a problem. And I'm going to take just a moment and I'm going to show you what that is. Okay, so I have the data sheet for the GAL 22 V10 and the GAL 16 V8 pulled up. And last time on the former video for the programmable logic that I uploaded last week, I talked about extensions and how some extensions don't work. And I have to admit I made a mistake. Doesn't happen very often, to my credit. I'm just joking about that. It happens all the time. But I did make a mistake, and it has to do with the use of the extensions. So before I talked about the extensions AR and SP, where it concerns the output logic macro cells. And specifically what that has to do with is the asynchronous reset and the synchronous preset. Now, the GAL 22 V10 actually has these. And when we were doing that last video, we were actually using the 16 V8. And if we take a look at the 16 V8 and its macro cell, it does not have the asynchronous reset or the synchronous preset. And if we actually look at, where's that at? Yeah, it doesn't even mention those two in here. So that was a mistake on my end. I didn't actually read that before I uploaded the video, and had I actually taken the time to figure that out, I would have known that. Like I said, I don't do a lot of registered logic on the PLDs. It's just not something I need a whole lot of use with. Most of the time, if I do need it, it's mostly just to divide a clock cycle in half or something along those lines. So I only need 1 or 2 pins. I just need enough to make it work. But this is something that we will have to take into consideration with this. So what we would have to do in order to make this work is all of these outputs here. We have to set the asynchronous reset and the synchronous preset. And an easy way of doing that would be to do this, I believe. Well, I'm starting off wrong already. So Q0 through Q7 dot AR equals binary 0. And the same thing here. So Q0 dot dot 7 dot synchronous preset equals binary 0. Okay, so if we compile this at this time, we shouldn't have any problems with this. So we're going to go ahead and save it, and we're going to try compiling it. We did get 2 warnings. There is no expression assigned to SB, so that is something that we need to take into consideration, as well as for DOUT. DOUT, we also need to do that. So let's go ahead and do that now. And then DOUT, not Doug, DOUT. You can tell I'm used to typing my name. Did it again. I get in a hurry. I will say that. I'm not a very patient man whenever it comes to typing, or many other things. But now if we save this and we compile it, 0 warnings, 0 errors. So next thing that we're going to do is we are going to pull up WinCUPL, and I'm going to get all of the signals preloaded, and I'm going to generate some states, and I'm going to show you the output of this PLD. Okay, so as soon as I am back, we will take a look at that. So after thinking about this just a little bit more, we actually don't need the start bit register. The reason for that being is because we can just go ahead and preset the serial output. So I've renamed some stuff and I've changed the equation here. Now the serial output is going to latch high when Q7 is high and parallel load is high, or whenever parallel load is low. So by doing that, we can preset that start bit. The same thing up here, I went ahead and got rid of the start bit and just renamed some stuff, and it's ready to go now. I've already saved it and compiled it. Compiled successfully. We have WinSim up, and we are going to go ahead and simulate it now. We're successful, and as you can see, we latched our data and we're shifting it out. So as the clock cycles, we can put data onto the data bus, and we can latch the parallel load, and doing that latches the data into the Q outputs, and it also sets the start bit on the serial out. Now whenever we cycle the clock, as you can see, the data shifts down, and it shifts out the it's the 55 hex that I have on the data bus here. So we have the 0 bit and the 7 bit here, so 1 0 1 0 1 0 1 0. It just alternates back and forth. That's a great thing about 55 hex and 55 hex and AA hex. They just alternate bits, so you can use that for testing. But it works. It simulates great. We don't need that start bit register, as I mentioned before. We're just basically latching the data over, and that is essentially how you build a shift register in WinCUPL or CUPL or whatever you want to call it. Feel free to steal that code. You're more than welcome to. I don't know, you may need a shift register and not have one on hand, so, but we can also change this as well. So if we wanted to shift this out, least significant bit first, we can change up the order and have the serial output read from Q0 and Q1 read from Q2, and there's a couple different ways that you can do that. And if you do it the right way, you could probably either make it shift left or shift right if you wanted to, but whatever the case, it's the basis is there, and now you understand a practical application for programmable logic. The things that you need to be keeping in mind whenever you are designing these circuits, and you can get as crazy with this as possible. You just have to remember it all comes down to your equation, the logic you are using to determine whether or not the output is going to be high or whether or not it's going to become low. It all comes down to how you do it. Now you also have to keep in mind that you can't determine both. So if I were to try to, let's say I wanted to set Q1D, but I wanted to set it not equal to, let's say, let's do something obvious. So not Q0 and PL. If I save this, it's going to shoot me an error. See? And the reason is because that expression has already been defined. You can only assign either a positive output or a negative output. You can't define both. So that's where you have to get creative with your equations. So that's it for today. I hope that you enjoyed the video. I would ask you to subscribe if you enjoyed it and you want to see other videos like this. I would like for anyone to leave a comment if they have anything to add or have any questions. I'd be happy to answer them as best as I can. If you haven't checked out the website, retrodepot.net, please do so. I tend to post things on there that do not get uploaded. And of course, if you like any other type of media that I might share from time to time, you're welcome to either hit me up here or there and request more of it. And at last, I'd just like to say thank you for taking the time to watch, and I hope that you learned something, and we will see you next week.